In this talk, I will guide you through stimulating and analyzing a mirror 101 model. The mirror model is widely used for time series forecasting. It combines three components: autoregressions, AR, differencing I for integrated, and moving average MA. We will begin by stimulating a mirror 101 time series, then fit the model to the stimulated data, finally assess the model diagnostics, including a Young book test. First, we stimulate a time series using a mirror 101 process. This model contains one autoregressive term AR and one moving average MA without differencing. The AR coefficient is 0.5, then the MA coefficient is 0.7. In a stat model, the autoregressive AR coefficients are defined with the sign conventions that includes a negative sign for elect terms. In the programming curves for an AR1 process with a coefficient of 0.5, the array is 1 minus 0.5, representing the polynomial 1 minus 0.5 times L, where L is a operator. The moving average MA coefficient are defined with a positive sign for MA1 process with a coefficient 0.7. The array is 1, 0.7, representing 1 plus 0.7 times L. The Augmented-Stigley-Fuller test, the results of this test is going to check whether the process is stationary. Have you seen the analysis here? The ADF statistics is minus 9.174, and the p-values is 2.34. And finally, the critical values on the 1% significant level, we have minus 3.436. For the 5% level, minus 2.86. Finally, 10% significant level, we have minus 2.56. The ADF statistics is significantly negative. More negative ADF statistic indicates stronger evidence against the null hypothesis of a uniroot, suggesting that the series is slightly stationary. The p-values is abysmally small, which is much smaller than typical significant level on 0.01, 0.05, and 0.1. This suggests a strong evidence to reject the null hypothesis that the series contains a uniroot. Therefore, the series is slightly stationary. And finally, critical values. The value is lower than all the critical values at 1%, 5%, and 10% levels. This further confirms that the time series is stationary. Now we move on to look at the optocorrelations and partial optocorrelations analysis. To further investigate the characteristics of time series, we plot the optocorrelation function ACF and partial optocorrelation function PACF. This plot helps us understand how the data are correlated at different lags. The lags are gradually decreased in the ACF plot, followed by a cutoff point in the PACF plot. Therefore, the process has an AR1 component for determining the order of MA process. The PACF plot shows a gradual decrease, followed by a cutoff point in the ACF plot. Therefore, it is an MA process. Combining the result, we infer that it is an ARIMA 101 model. Next, we fit the ARIMA 101 model to stimulate the data. The model estimated with the following parameters, each offering insight into model's dynamics. First, constant. The model intercept or constant term, it estimates as 0.1359 with a p-value of 0.222, indicate that it is not statistically significant at typical significant level of 0.05. Therefore, this constant may not be necessary in the model. ARL1 the coefficient of the lat1 regressive AR terms. The value is about 0.5095. It means that the series pass value positively influences the current value. With a p-value of a very small number, this term is statistically significant. The coefficient on lat1 moving average MA term, the value is about 0.7228, indicates a positive relationship between the path shock and the current value of the time series. This coefficient is also statistically significant because, again, the p-value is a very small value, which is much lower than 0.05. The estimate variance of the residual error term, the variance is calculated as 0.99989 with a p-value of a very small number, which is much smaller than 0.05, indicating that the model's residuals have a relative stable variance. Now we look at more model diagnostics. The additional output from the model fitting process provide crucial information about the model's performance and suitability. Here's an explanation of each component. Why here? This is the dependent variable, which in this case is stimulated ARIMA time series data. The number of observation we have is 1,000. This indicates the number of data points in this time series, providing a substantially sample size for reliable analysis. Again, the model is ARIMA 101. The Pacific model includes one autoregressive term, 0 different things, and one moving average term. This combination helps in capture the linear relations and short effects in the time series. Log likelihood minus 1419.240, a measure of likelihood that the model fits the data, where higher, less negative values suggest a better fit. And then we're looking at the information criteria, AIC Akahike information criterion 2846.481. A lower AIC value indicates a better model fit with a sufficient complexity to capture the data dynamics without overfitting. BIC Bayesian information criterion 2866.112. BIC is similar to AIC but with a stronger penalty for models with more parameters. Again, a lower BIC value indicates a better model fit with a sufficient complexity to capture the data dynamics without overfitting, like the descriptions of AIC. Finally, we have the Harlequin information criterion. The value here is 2853.942. This criterion strikes a balance between AIC and BIC, offering a different perspective on model complexity. The next two items I want to discuss is sample. Everything on the screen is, again, is 0 to 2000s. We have 1,000 data points to give a reliable analysis regarding the process we are looking at. And then finally, we're looking at the covariance type, the outer border of gradients. This method estimates the covariance of the model parameters, ensuring robustness in the parameter estimation. So what are the major interpretations of these results? So the model diagnostics suggests that the ARIMA 101 is adequately capturing the underlying patterns of the time series. The AIC-BIC values are crucial for comparing the model against alternative specifications. Typically, a model with lower AIC-BIC values is preferred, and it suggests a better trade-off between goodness of fit and simplicity. Now, we're looking at more model diagnostics. The additional output include important diagnostic statistics for a mirror model, which can help us assess the model adequacy. Below is the interpretation of key tests and statistic. as you've seen on the screen, Young book test L1. The Q statistic here regarding about this test is 0.04. The probability of this statistic is 0.83. The interpretation of this test is about checking whether there's a significant autocorrelations in the residuals. Again, when you look at the p-value 0.83, significantly above 0.05, indicators we fail to reject the null hypothesis of no autocorrelation. This suggests that the residuals are uncorrelated and the model is well fitted in terms of capturing the autocorrelation structure. Jacobi test, the statistics, JB statistic is 0.19. The probability of JB is talk about 0.91. This step check whether the residual follow normal distributions. The higher p-value indicates we fail to reject the null hypothesis of normality, suggesting the residuals are normally distributed, which is definitely a desirable property for the bell-fit model. Finally, when we talk about heteroscedasticity H-test, the H statistic is about 1, probability is 0.97. This test check for change in the variance of these residual over time. A high p-value suggests that the residual exhibit constant variance. Homoscedasticity indicate the model is adequacy. The final point is the skewness and kurtosis. The skewness is minus 0.03, indicates a near symmetric in the residuals. And also the kurtosis is 2.99, close to 3, suggests a normal distribution for the residuals. This matrix support that the residuals are well behaved, further confirming the model suitability for the data. Now, the last bit of our analysis. In the first graph, the histogram of the residuals roughly follows a normal distribution, which supports our assumption of Gaussian white noise and correlated residual with a normal distributions. In the next graph, the AFC and PACF plots of the residuals show that all less values are within the threshold of plus minus 1.96 over square root of 1,000, where 1,000 is the total sample size. This indicates the residuals are likely uncorrelated, consist with the white noise. In conclusions, we successfully stimulate an ARIMA 101 time series and fitted the model to the data. The model diagnostics, including the Young-Bock test and the Jacobi test, indicate the residuals are well behaved, and the model adequately captures the structure of the time series. This robust fit allows us to confidently use the model future forecasting or to further refine the model's parameters for even better performance. Thank you for your attention. I see you all for the next one.